Welcome back. Now, in the previous section, you may have seen that I derived a 6 by 6 stress matrix. So, stress and strain gets related through the elastic constant. That is an important fact. But it looks very horrendous, it looks very complicated. But if you look at different cubic symmetry as well as isotropic material, as I said in the last section, it may just come down to only 3 elastic constant that you need to worry about, C11, and they are all connected with the direction. So, sigma 11 is again this Voigt convention, where 1 is 2 and 3 are the 3 x, y and z direction, and 1 is the principal direction, just like sigma xx. And so, we will go through that expression later, but this is what happens, that you are looking at stress and strain. So, this is called elastic property. So, this is called linear elasticity, primarily because this relationship is linear. As you increase the stress, the strain increases, that means the expansion happens. So, this stress strain curve is the elastic curve, and this is what we are looking at, the elasticity. Now, there is another part which is called shear, because we are looking at the cross terms. So, we are also looking at the shear strains. So, this is the principal strain, this is the plane which is perpendicular to that. So, because of that you have another force coming new, and that is where you can define the shear parts of 1, 2. So, if you look at sigma xx, there is sigma xy and sigma xz, those are defined by nu. So, if you look at this elastic term, this is a strain. We are now looking from the strain perspective. So, let us say you take a particular rod and you are straining it, and this E 1, 2 and 3 are the strains in 3 direction. Then you can also create a strain matrix with the constant that we have looked at. So, if you want to calculate the strain, and if you know the elastic constant, it becomes a reciprocal relationship, which is identified here. So, in this case you can see E11, eta 22, eta 33, eta 12, eta 13, eta 23. Now, in this case again this is an isotropic solid. So, you are looking at a lot of terms become 0, because they cross each other, they balance each other. But in this case the only term that are important are sigma 11, and these are the principal directions. So, we are looking at 9 plus about 3 other what we call is the elastic constants, and then we multiply that, and this is 1 over E, which is multiplying that by some of the shear components, that gives you the stress matrix. Plus, if you have external forces, then you can also add that. So, this is how you deal with that. So, if you look at, there are 2 matrices that are called elastic constants. So, compliance, when the stress gets related with strain, that is called compliance matrix, which is given byCijkl. Now, you are saying why you use 4 subscript. So, sigma ij is defining the stress, and resultant strain is defined by Kl. And because the elastic constant relates between ij and Kl, it has to have all 4. So, if you look at this elastic constant sigma ij and eta Kl is related by sigma ijkl. And that is where, if you look at the generalized anisotropic, where obviously every direction has a different elastic constant, then all 36 elastic constant becomes available. 6 by 6 matrix, 36 elastic constant, and that is where what you are looking here is sigma 1 1 2 2 3 3 2 3 1 3 1 2. Then you have equivalent elastic constant, which are called compliance, C11, C12, C13, etc. You can derive that, and equal to the strain in the principal direction. But if you look at in the cross directions there, because as you saw earlier, there are 2 forces working in the cross direction. One is going in one direction, another one is another. So, there are 2 strains here, that is why you multiply it by 2. So, 2 eta 2 3, 2 eta 1 3 and 2 eta 1 2. So, with that understanding, another matrix, when you reverse it with the strain, that is called stiffness matrix. So, this matrix of elastic constants is calledCijkl, which is the compliance, and this one is called stiffness matrix, and these are the stiffness constant, which are nothing but reciprocal of the elastic constant. But in this case, you start with you then want to calculate the strain, and so you have Sijkl connected with the stress which you are applying, which becomes Kl in this case. So, you can switch between the two depending on your situation, and that is how we move forward. An isotropic solid have one of the issue is thatCijkl is equal to Cjikl, and these relationship of equality are not working if there is some anisotropy. That means there is directionality. So, now directions become important. You can't say sigma 1 1, sigma 2 2, sigma 3 3 are same. So, now in this case you have to have strain in principal direction with stiffness matrix, as you can see here, and all of these components are important. So, you have 6 components here for that kind of situation. Now, you can also have solids which are orthotropic, that means they have we have symmetric planes. So, in x direction there is a symmetry, or y direction there is a symmetry, and you will see that symmetry becomes very important in terms of elastic constants, because that can reduce your number of elastic constants. For example, cubic crystal has a symmetry in all 3 directions because it is cube. But if you look at orthotropic, there may be, as you are seeing here in the picture, that this has a fiber direction is in, let us say, in y direction or x direction. So, it will have different properties in the fiber direction as compared to the cross section or the perpendicular direction to that. And so, that is where orthotropic solid come into being, but the generalized mechanism is this, where you are looking at the 36 going down to 9 plus 3, about 12 elastic constants for anisotropic, and for isotropic it goes to 3, which is C 1 1, C 1 2, sigma 1 1, sigma 1 2, and sigma 4 4. So, now we come back to our problem of failure of pair potential, as we understand earlier, that pair potential essentially say sigma 1 2 is sigma 4 4. So, what they are saying, because it is spherically symmetric potential function, that creates this anomaly which is called Cauchy anomaly, which is artificially it makes C 1 2 equal to C 4 4, while in most of the real metals C 1 2 is not equal to C 4 4. And that is where also that is where we said EAM potential is able to look at that. But now that you understand C 1 2 and C 4 4, I want you to look at the data on your slide. So, if you look at Lennard-Jones, for Lennard-Jones material where there is completely isotropic spherical potential is workable, you can look at argon, and if you look at, now we are looking at the vacancy formation and cohesive energy respectively. So, this is the energy for vacancy formation, this is the energy for cohesive, and you are looking at the ratio of that, which is equivalent to C 1 2 and C 2 2, because C 1 2 is almost like vacancy formation, and C 4 4 is shear, which is the cohesive energy. So, now if you look at an argon, C 1 2 over C 4 4 is 1.0, and so if you look at a Lennard-Jones function for argon is 1.1. If you do the real calculation of the energies, 0.95. So, for argon, Lennard-Jones function works, no issues, no problems, because C 1 1 is equal to C 4 4, because the ratio is 1.0. However, as you move to, let us say, even nickel, which is a different substance. So, you see there is even in krypton there is 1.0, and it becomes the ratio experimental 0.66. So, we are looking at and we are also looking at the melting temperature, melting in this case as well. So, but just focus on C 1 to C 4 4. So, now you can see the comparison between the vacancy formation energy and cohesive energy diverges quite a bit. So, in actuality for the nickel it should be close to 0.31, but it is predicting 1.2. So, Lennard-Jones function stop working at certain point, and that is where you have to use multi-body potential, as we had described in terms of EAM potential. So, now what we are going to look at is we are going to look at some of the ideas about atomic stress, and then how we can look at the pair potential and why the pair potential do not work, and we will talk about that and get into the atomic stress. Thank you.